So far in the computer architecture course, we have discussed instruction pipelining and superscalar processor design. So in order to improve the overall performance of the system, the processor microarchitecture has advanced from the in-order scalar pipeline design to the out-of-order superscalar processor design. And also we have gone for deeper pipelines in our processor design. Once we have deeper pipelines, so we can have more number of in-flight instructions in different stages. So as a result, we can improve the overall throughput of the system. At the same time, in the superscalar processor design, we consider parallel pipelines. So as a result, we can actually issue multiple instructions in every cycle. So once we consider this multi-issue superscalar processor with a deeper pipeline, so our total number of in-flight instructions will be significantly higher, so that by using the out-of-order execution mechanism supported by superscalar processor, we can identify independent instructions and execute these independent instructions on various functional units available with the system. So because of this deeper pipelining and multi-issue, we can improve the performance of the system significantly compared to an in-order the scalar pipeline. So again, in order to further increase the processor performance, we can go for even much more deeper pipelining, and also we can go for an aggressive superscalar mechanisms. So when I say aggressive superscalar mechanisms, we can actually consider a speculative execution, we can consider advanced branch prediction mechanisms, and we can increase the issue width of the superscalar processors and so on. But when we are going for deeper pipelining concept as well as the aggressive superscalar mechanisms in our system, the complexity of the system is going to increase significantly. And in reality, the amount of performance whatever we get because of this aggressive superscalar mechanisms as well as the deeper pipelines is not that high as compared to a moderate pipeline superscalar processor design. So this is called as the ILP wall. So the ILP wall says the returns whatever we get is not much higher compared to the amount of effort we put in. So in this graph, the x-axis shows the effort we put and the y-axis shows the performance we get in return. So we move from scalar in-order processor to a moderate pipeline superscalar processor which supports out-of-order execution, and we increase the number of pipeline stages in our superscalar processor, and also we add this aggressive superscalar techniques such as speculative execution and so on. But we can see here after this stage, the amount of performance improvement compared to the previous design point is not significantly increasing. In other words, this performance curve is almost flattened here, and as a result, we may not get a significant benefits if we go for this complex superscalar processor designs and so on. And this is mainly because of couple of factors associated with our the applications. One thing is the applications may not have significant instruction level parallelism. So that is the reason why this is called as an ILP wall, because if the applications are not having enough instruction level parallelism, even if we use aggressive superscalar mechanisms, we cannot fill all the issue slot with useful instructions to compute. So as a result, once we don't have useful instructions to issue onto functional units, so functional unit cycles will be wasted, and as a result the overall performance will not be improved significantly. So that we can show here in this particular the diagram. Here this is a 4 wide superscalar processor which issues 4 instructions at every processor cycle. So we have 4 functional units, and the maximum ILP we can exploit with this 4 wide superscalar processor is a 4. So that means like we can issue 4 instructions every cycle to our functional units, and also we assume that all the functional units are properly pipelined. So even when we have a properly pipelined functional units and our system can support 4 instructions executing simultaneously every cycle. Even then, if you see in this diagram, there are several empty boxes, and each of these empty box indicates that the functional unit in that particular cycle is sitting idle. And this is mainly because applications may not have enough instruction level parallelism, and also when we are executing some instructions which may require long latency event. For example, if there is a load instruction that misses in the L2 cache or L3 cache. So, in order to service a load request which misses in the L2 cache, we have to go to L3 cache, and which may take 10 to 20 cycles. So, as a result, unless we supply the data from the L3 cache for this load instruction, we cannot execute any instruction which is actually requiring the data supplied by this load instruction. So, as a result, we are not able to we may not able to identify independent instructions that can be scheduled on these functional units in the appropriate processor cycle time. So, because of that, we will get lot of the cycles where functional units are not efficiently utilized. So, as we have more empty boxes, that indicates that more number of functional unit cycles are wasted, and that in turn results in the performance degradation. So, in summary, applications may not have a significant instruction level parallelism to utilize by using our aggressive very deep superscalar processor, and also the superscalar processor design cannot tolerate this high latency events, because once the application is not having enough instruction level parallelism, we cannot hide the latency incurred by this the load requests which miss in the L2 cache or L3 cache and so on. And also another thing is, the superscalar processor always work with a single thread. At any point of time, it can fetch the instructions from a single thread, and these fetched instructions will be decoded, and these decoded instructions will be dispatched to the functional units, and they will be executed. So, as a result, if that single thread is not having enough instruction level parallelism, we cannot get a significant performance improvement with the superscalar processor. So, our objective is to improve the performance of the system significantly by using some other mechanism. So, in other words, utilize these idle functional units which are sitting idle because of the lack of ILP in our programs, and in order to utilize these functional units, what we have to do is we allow multiple threads to share these functional units so that they can execute their instructions on these idle functional units. So, as a result, the instruction execution will be overlapped across multiple threads, and as a result the resource utilization will be improved, and the overall throughput of the system can be improved. So, in order to improve the overall performance of the system by making the efficient use of our functional units, we have to go for the other method that is called as the multi-threading, and this multi-threading is part of thread level parallelization. So far we have discussed instruction level parallelization as part of superscalar processors. Now we move on to a different architecture concept, that is the multi-threading, where we actually exploit the thread level parallelization. But of course, the complete thread level parallelization can be exploited as part of our multi-core architectures that we are going to discuss in the next module. So, in the multi-threading systems, we deal with threads. A thread is nothing but a control flow of execution, and so given a program, a compiler can divide that program into multiple threads, or the programmer himself can write a multi-threaded program. And once we have these multiple threads, and each of these threads is called as a software thread, and a program can consist of 100 software threads, but in order to execute these software threads on the underlying hardware, we need to have the support for this multi-threading. So, as a result, we need to have a system that takes care of the execution of these threads on its resources. So, for that, actually we have to consider a thread context. The context of each thread can be identified based on the program counter as well as the architectural registers. So, whenever there is a switch between one thread to another thread, we have to save all the contents of the architectural registers as well as the program counter, so that we can start executing the next thread, and once the next thread completes its computation, then we can again come back to the previously switched out thread by restoring these values, the PC content and the architectural registers are back to these registers, so that we can resume the suspended thread execution. So, as a result, our hardware needs to have a support for executing multiple threads simultaneously. So, for that effectively we need to have multiple program counters, we need to have multiple architectural register the files and associated rename register logic and so on. So, effectively if a system is supporting multi-threading concept, that means like if the system that can execute multiple threads on it, then it has to have support of multiple program counters as well as the multiple architectural register file. And once we have this PC and architecture register files replicated for each of the threads, then we can efficiently execute multiple threads on the system by switching in and switching out of the threads. So, in a conventional processor, we typically have one program counter and one set of architectural registers, and this entire thing is called as the thread context. And this conventional processor is actually dealing with only one thread at any point of time. And once we have a single thread context for this hardware, then at any point of time it can execute only one thread or the instruction from a single thread. And if you see the instruction stream, so it always takes the instructions from the single thread and execute. Because we are dealing with a single thread and this single thread may not have enough instruction level parallelization. So, as a result, because of the dependencies among the instructions, we may have the pipeline stalls or bubbles in the pipeline execution. So, as a result, you can clearly see here these white boxes indicates that the functional unit is not utilized in that particular processor cycle. So, there are many empty slots, mainly because our thread is not having enough instruction level parallelization, and also because we are executing instructions from a single thread. So, as a result, we are not able to utilize these underutilized functional units. So, in order to make use of these underutilized functional units, what we have to do is we have to go for a system that is supporting multi-threading. So, when we consider a system supporting multi-threading, now we can see here we have a single processor, but this processor has now support for 4 hardware threads or thread contexts. So, each hardware thread has associated PC and the architectural register file. Of course, we know that a processor is not just a collection of the PC and the architectural register file. There are several other resources associated with the CPU or the processor. So, now when we have a multi-threaded processor, all the other resources of the processor will be used by all these the software threads which are executing on this the hardware threads. So, effectively other than this PC and the register architectural register file, all other components of the processor can be shared by the software threads which are running on this the hardware threads. We can also call the thread context as a hardware thread. So, now in this particular design, we have a single processor which has a support for 4 hardware threads. So, that when a programmer writes a multi-threaded application with 100 software threads, and if he wants to execute this 100-threaded multi-thread program on this particular processor, so he can execute only 4 threads at any point of time, because this system is supporting only 4 hardware threads. So, effectively we have to map 4 software threads onto this 4 hardware threads, and at any point of time it can execute only 4 software threads. Again, depending on the type of multi-threaded processor design, we can make only one hardware thread active at any point of time, or we can make all the hardware threads active simultaneously. So, that we are going to discuss in the next file. So, now once we have a multi-threaded processor which has multiple thread contexts, then we can clearly see here the instruction stream is actually taking instructions from different software threads that are executed on different hardware threads. So, for example, in the first cycle we are taking an instruction from a software thread running on this the hardware thread, or effectively by using this PC which is pointing to the one instruction in the software thread that is associated with this, and we fetch that instruction and execute that instruction. And in the next cycle we can move on to the second software thread which is mapped onto this hardware thread, and we, by using this PC, we will fetch the instruction from this software thread and execute that instruction. And in the third cycle we can fetch an instruction from a software thread mapped onto this hardware thread, and so on. So, as a result we can minimize the wastage of functional units by exploiting thread level parallelization. So, that means like when one thread is blocked for a long latency, or even there is a L1 cache miss or something which takes, even if it is taking 2 to 3 cycles, so dependent instruction cannot be issued to the functional unit. So, as a result we can mask these the cache misses and so on, or the miss penalties by scheduling instructions from different threads. So, as a result, by exploiting thread level parallelization, we can make use of all the functional units efficiently, and we can improve the overall performance. Now, you can clearly see here, for example, this instruction which is from this software thread mapped onto this hardware context, if it incurs L1 miss, which is going to take 6 to 7 cycles to get the data from L2. Meanwhile, while this instruction is sending its load request to L2 cache, and the L2 cache is going to supply the data, meanwhile we can actually schedule instruction from the other threads onto this functional unit. So, effectively the latency incurred by this the load miss for this software thread is overlapped with the execution of the threads from the other hardware context. So, as a result we can hide the latency because of this cache misses, and that is going to utilize all the functional units efficiently, and we can improve the overall performance of the system. So, as a result once we have the multi-threading support in our system, we can exploit the thread level parallelization, and we can improve the overall performance of the system. So, once we have a multi-threaded processor, now we can see like what resources will be shared, what resources needs to be replicated, what resources can be partitioned in our processor. A processor consists of a collection of resources, and starting from the program counter, the architectural register file, register renaming logic, reorder buffer, load store buffers, fetch queue, decode queue, dispatch queue, issue queue, the retire queue, and similarly the cache memory L1, L2, L3 caches, rename registers are physical registers, and functional units. So, several resources are available with the processor, and if the processor is supporting multi-threading, now some of these resources can be shared by all the threads associated with the processor, but some resources needs to be replicated. Some resources cannot be shared by multiple threads, such as program counter, architectural registers, and rename register logic, because we know that the control flow of a thread will be uniquely determined by the program counter content as well as the architectural register contents. So, as a result we cannot share these resources across multiple threads. We have to replicate these resources if we want to support multiple threads in our processor. For example, if we consider a 4-threaded multi-threading processor, then we need to have 4 PCs, 4 architectural register files, we need to have 4 rename register logic units, and similarly if you are considering an 2-way multi-threading, then we need to replicate these units 2 times. And whereas in the case of the reorder buffer, load store buffers and several other queues, we can partition these things across the multiple threads, and this partitioning can be done statically or dynamically. We can equally divide our ROB entries for all the threads of our system, or we can divide the load store buffers equally across all the threads and so on. When I say thread, here this hardware thread associated with our processor, and similarly we can divide the queues across all the threads of the processor. And in the case of cache memory, the physical registers, execution units and so on, we can actually share these units across multiple threads. The reason is because multiple software threads running on your hardware threads of a multi-threaded processor may be related in somehow, because all these threads may belong to a same process, and as a result there may be the data sharing across multiple threads of a process. So, as a result we need to consider this cache memory shared across multiple threads, and similarly we can consider this physical register shared across multiple threads. And of course, the execution units we have to share, because we cannot have separate execution units for each of the threads. If we have separate execution units, then the execution unit utilization may not be significantly improved. For example, if you consider one thread is actually executing integer operations and the other thread may be executing only floating point operations. And now what is going to happen is, if you are considering a separate execution units for each of the threads, and we can consider one instance of integer unit, one instance of floating point unit for each of the threads in our design, where we consider separate execution units across the multiple threads. If it is so, then when I am executing a thread which is executing only integer operations, then the floating point unit associated with that thread will be underutilized. Similarly, if I am executing instruction from a floating point thread, then the integer units may not be utilized. So, as a result, if we share all the function units across all the threads, then the resource utilization will be improved, and as a result we can improve the overall performance of the system, and we do not incur significant hardware overhead because the functional units are shared across multiple other threads. So, after discussing this resource sharing across multiple threads, now we will see like what are the different type of multi-threaded processor designs we can consider. So, our underlying processor is consists of 4 hardware threads, for example, and we have a pipeline design for processing our instructions. So, in order to consider different multi-threaded processor designs, so we have to consider these key characteristics. So, which thread to be selected for executing next instruction? Because we have 4 hardware threads and each hardware thread will have some software thread mapped onto it. Now, whether we have to fetch the instruction from the software thread mapped onto this hardware thread, or from mapped onto this hardware thread, or a software thread mapped onto this hardware thread, or the other one. So, how do we select? Whether we have to issue instructions only from one software thread at any point of time continuously and then move on to the other one, or whether we have to apply a round robin policy across all these threads and then execute instructions one from one thread per cycle and so on, or otherwise we have to consider all these hardware threads to be active simultaneously and so on. So, that means like our thread scheduling policy is going to determine our multi-threaded processor design. If we consider at any point of time only one thread needs to be servicing the request, then we will come up with one type of multi-threaded processor design, or if we consider multiple hardware threads can be active simultaneously, then we can come up with a different type of multi-threaded processor design and so on. And similarly, once we have the instruction pipelining, now whether this instruction pipeline can be partitioned across this multiple threads, or whether we have to consider no partitioning across multiple threads. So, that also is going to determine what type of design we have to come up with. So, once we have these key characteristics to decide on different type of multi-threaded processor design, we can consider 3 different multi-threaded designs. One is a coarse grain multi-threading CGMT, the second one is a fine grain multi-threading FGMT, and finally, the last one is a simultaneous multi-threading SMT. So, we are going to discuss these 3 in detail in the coming files. So, we start with the coarse grain multi-threading. As the name suggests, coarse grain. So, we always execute instructions from a single thread continuously, and this will continue till a point where any instruction from this thread is incurring a long latency event, such as an L2 cache miss or L3 cache miss. Whenever such thing happens, then because in order to service this long latency event, we incur significant amount of processor cycles, and rather than wasting the processor cycles for such significant amount of time, what we can do is we can issue instructions from a different thread. So, that means whenever there is a long latency event occurred on a currently running thread, then we switch out that thread and then we resume execution from a different thread. So, that means in this coarse grain multi-threading, our thread scheduling policy is like this. We switch threads only on long latency events. Why we are considering long latency events only? Because this is also determined by our pipelining partitioning method. In this coarse grain multi-threading, we consider our pipeline will not be partitioned across multiple threads. So, that means whenever there is a context switch is going to happen for a currently running thread, then we have to flush all the instructions related to that particular thread starting from the instruction which incurred this long latency event, and after that we can resume instructions from the different thread by fetching the instruction from the different thread. So, as a result, there will be significant amount of pipeline stages wasted in this process, because our execution is happening somewhere in the middle of the pipeline and fetch is happening at the front of the pipeline. And if we consider a deeper pipeline design, then the number of pipeline stages between the fetch and the execute will be significantly higher, and as a result, if you are always switching for a low latency events in this coarse grain multi-threading design, then we are unnecessarily wasting processor cycles, and which leads to a significant degradation in the performance. So, as a result, we have to switch between threads only when we encounter long latency events, and so as a result, if this long latency event is incurring a significant amount of time to service, then it is always better to go to a new thread even when we incur some number of pipeline stages wasted in the process of flushing out and then fetching new instruction from the new thread. In other words, in the coarse grain multi-threading design, we always consider context switch only for long latency events, and this long latency event is going to take a significant amount of time, which is much higher than the number of pipeline stalls that incur because of flushing out the pipeline and fetching new instructions from a different thread. And because of this thread scheduling policy as well as the flush on a context switch, this coarse grain multi-threading can tolerate only the long latency events. It can tolerate only the long latencies incurred by our the instructions executed on the processor. And if an instruction which is incurring, let us say, 2 cycle latency, which is going to create a stall in the pipeline by 1 cycle or 2 cycle, then this design cannot tolerate those latencies, because for a low latency events we are actually not taking the context switch. So, as a result, we will waste those processor cycles in it. So, in order to reap in most benefits, so we have to consider 2 to 4 thread context in our coarse grain multi-threading design. And so, in this particular example, we are considering a 4 wide processor. So, as a result, at every cycle we can issue at most 4 instructions onto 4 functional units. So that means our maximum ILP that we can achieve here is 4, but because of the dependencies among the instructions of a thread, so we may not issue 4 instructions every cycle and so on. So as a result, in some of the processor cycles there are some the functional units which are underutilized, and also because we are actually issuing instructions from a single thread continuously, and only when there is a long latency event then we move on to a different thread and we execute instruction from the second thread and so on. Here the color coding indicates that we are actually executing instructions from 4 different threads. So continuously we execute instruction from one thread and then move on to other thread because of a long latency event incurred by one of the instructions executed earlier here, and after that we execute instruction from a second thread, and again there may be a long latency event, so we can move on to a different thread, or otherwise we can start executing from the previously context switch thread and so on. And this type of design actually considered in IBM Northstar Pulsar processor, but the current processors are actually not using this type of design, and it is simple to implement and it improves the performance or in terms of the throughput, and it is easy to design. So as a result it is not going to take a significant cost, because here we are considering only fewer number of thread contexts. So as a result our hardware cost also is not significant, and because here actually we are taking a context switch on long latency events and we are stalling on low latency events, so it is actually designed for in order process and it is not suitable for out of order processing. So now we move on to the second design, where we will consider a fine grain multi-threading. As the name suggests, we actually switch between threads at every cycle in a round robin fashion. If we have, let us say, 4 threads in our processor, then in the first cycle we issue instructions from thread 1, in the next cycle we will issue instruction from thread 2, in the third cycle we issue instruction from thread 3, and in the last cycle we are going to issue instruction from thread 4, and in the fifth cycle again we will go back to thread 1 and will continue. So effectively we are actually rotating between all these available threads, and by doing that we are going to actually hide the latencies incurred by our instructions. So in this fine grain multi-threading we switch between threads at every cycle, and because at every cycle the thread context will be changing, so as a result we have to consider dynamic pipeline partitioning across multiple threads. So effectively here one pipeline stage we may be executing an instruction from one thread, in the next pipeline stage we may be executing instruction from the other thread. So effectively in this fine grain multi-threading concept, our overall pipelines will be shared by instructions from different threads. One pipeline stage may be used by one thread, the other pipeline stage may be used by instruction from the other thread, the next pipeline stage may be used by instruction from the third thread, and so on. Effectively here we are actually sharing our pipeline stages across multiple threads, and we are also not considering any flush mechanism as that was considered in coarse-grain mechanism. So as a result we are not going to incur any penalty also, and because we are switching between threads at every cycle, so this fine grain multi-threading can tolerate pipeline latencies as well as cache access latencies. When I say pipeline latencies, so there may be an ALU instruction which is going to take 3 cycles to complete its execution, so that also can be tolerated here. Similarly there may be a load instruction which is going to take a 4 cycle latency to get the data from L2 cache, that also can be tolerated by scheduling instructions from the thread at appropriate time. But in order to hide this low latency as well as the high latency because of the cache misses or the instruction execution, so we need to have enough number of threads in our system. So once we have enough number of threads, we can switch across this large number of threads, so that we can hide the latencies associated with this long latency events or short latency events. And the processor which actually implemented this type of fine grained multithreading is UltraSpark T1 Sun Niagara 1 processor, and the current NVIDIA GPU processors also actually using this fine grained multithreading. And this conceptually simple to design, and it provides a high throughput as long as we have enough number of threads to support the overall computation. But the main disadvantage with this fine grained multithreading is the single thread performance is very poor. The main reason is, even though if I do not have any dependencies among the instructions of a single thread, because of this thread switching across multiple threads, and if the system has multiple thread contexts, so as a result I have to delay the execution of this particular thread, whatever I am interested in, because I will execute few instructions from this thread and wait for some time to execute instruction from the other threads, and only when my turn comes back and again I will execute instruction from my thread. So as a result, single thread performance may not be improved, and the overall performance of single thread will be significantly lower, but the overall throughput will be higher. So we are trading the single thread performance for improving the overall throughput of the system. And finally, we consider a simultaneous multithreading, and this simultaneous multithreading is actually considering fine grained multithreading as well as superscalar processing mechanism. So far in the fine grained multithreading and coarse grained multithreading, the underlying hardware keeps only one hardware thread active at any point of time. So while we are issuing instruction from one thread, the other thread will not issue its instructions to the processor. So as a result, we cannot exploit the thread level parallelism to a full extent. So but whereas in the case of simultaneous multithreading, we actually consider issuing instructions from multiple hardware threads simultaneously. And also the previous designs, that fine grained multithreading and the coarse grained multithreading, are actually not considering out of order execution. So here in this multithreading, we exploit the superscalar processing. So that is, we can execute instructions in out of order fashion by considering our register renaming part, by considering dynamic scheduling and other things. As a result, the simultaneous multithreading is actually built on top of superscalar processors. Because we are actually considering the fine grained multithreading concept, so we consider thread scheduling policy as a round robin here. We can switch between multiple threads at a cycle granularity, and we can share our pipeline stages across multiple threads. So that is what we are considering a dynamic pipeline partitioning mechanism, and we are not going to consider a flush mechanism here. And because we are considering the round robin scheduling as well as dynamic pipeline partitioning, so the simultaneous multithreading can tolerate the pipeline latencies as well as the cache access latencies, which may incur few cycles or which may incur 10 to 20 cycles. And in order to improve the overall performance, we need to have 2 to 8 thread contexts in our system, so that we can get the maximum benefits. And Intel Pentium 4 processor actually implemented this simultaneous multithreading under the name of hyper-threading. So here we can see, so in cycle 1 we actually issued one instruction from one thread, one instruction from the second thread, one instruction from the third thread, one instruction from the fourth thread. So effectively in a single cycle we issued 4 instructions, one from each of the threads, so that we can execute these instructions on available functional units. So as a result, our functional unit utilization will be improved. In the second cycle, again we can issue 4 instructions at max, because this system is supporting 4 issue, but because of the dependencies or because of are not able to find independent instructions. Here in this particular cycle, we issued only 3 instructions from 3 different threads, and this thread is not able to issue next instruction. Similarly, we are not able to find second instruction from any of these threads, and sometimes we can even issue all 4 instructions from a single thread also. So, effectively at each cycle we will see which thread can issue an instruction onto a functional unit, and if we can find multiple instructions from a single thread, we can issue those multiple instructions onto the functional unit, and we can improve the overall performance. So, as a result, at every cycle we will look at all possible threads and see which thread can supply instructions. A thread can supply 1 instruction, 2 instruction, or multiple instructions, and as long as we find some issue slot is free, then we can go to a next thread and see whether we can issue 1 instruction from that particular thread, and so on. So, as a result, we can minimize the resource wastage significantly, and the overall performance can be improved by using this simultaneous multithreading. So, the simultaneous multithreading can improve the throughput significantly, and it hides the memory latency. Even if we are incurring an L3 cache miss, we can hide the latency by servicing a request from different threads. So, as long as if a thread is waiting for some L3 cache miss to be serviced, we stop fetching from that particular thread, we stop fetching instruction from that particular thread, and we execute instruction from different threads. So, as a result, we can improve the overall performance. And here, because in this simultaneous multithreading, multiple hardware threads can be active simultaneously. So, we have to share our resources also. So, we have to have multiple fetch queues, we have to have multiple decode units, we have to have multiple the issue queues, we have to have multiple retire queues, and we have to partition our ROB across multiple other threads, so that they can execute their instructions without having any difficulty. And because the resource sharing is happening in the simultaneous multithreading, so we can consider either a static partitioning method, or we can consider a dynamic partitioning method, and depending on the application requirements, we can consider different proportion of our resources will be given to different threads. So, that is what can be considered in dynamic partitioning. And if you do not want this dynamic partitioning method, we can go for a static partitioning, where we can divide our resources equally across multiple threads, so that everyone will get equal share, and they can use these resources. So, again, so here, in order to consider this static or dynamic, we have to consider whether fairness is important for us or the performance is important, and depending on our requirements, we can consider either the static partitioning or the dynamic partitioning. But because here multiple threads are active simultaneously, and these threads can use the TLBs and the caches in a sharing mode, and because of that, there may be significant number of conflicts occur in the TLBs and the caches, and that may degrade the performance. So, as a result, when we are dealing with simultaneous multithreading, we have to consider the efficient sharing mechanisms in these shared resources, so that the performance degradation because of these conflicts can be minimized, and we can improve the overall performance of the system. So, in summary, we can look at different processor designs and see how each of these designs are making use of the functional units in each processor cycle, and improves the overall performance. So, if we consider a superscalar processor, because here instruction from a single thread will be issued onto the functional units, and because of a lack of instruction level parallelism, we may not efficiently utilize all processor cycles and all the functional units in each cycle. And in order to overcome this problem, we can go to a different design, that is called as a coarse-grain multithreading, where we can switch between multiple threads. Whenever the currently executing thread encounters a long latency event, we switch to another thread and issue instruction from the selected thread and continue execution. So, as a result we can minimize some of the resource wastage as compared to this superscalar processor. But again, in the coarse-grain multithreading, we are switching between threads only on long latency event. So, in order to further improve the overall performance, we can actually go for fine-grained multithreading where switching happens at every cycle. So, we fetch instructions from one thread in cycle 1 and we switch to a second thread and issue instruction from the second thread and will continue this process. But in a single processor cycle, we fetch instructions and issue instructions from a single thread. So, as a result, still in that particular thread, if we are not able to identify enough ILP, then we waste functional units in that particular cycle, and that is what we can see here. There are still some empty boxes that indicates that some of the functional unit cycles are wasted if you use this fine-grained multithreading. So, in order to further improve the overall performance or in order to further improve the resource utilization, we can actually go for simultaneous multithreading, where in each cycle multiple threads will be active and they issue instructions from the corresponding threads onto the functional units. So, as a result we can minimize the resource wastage, so that we can improve the overall performance. So, as we move from the superscalar all the way up to simultaneous multithreading, we can improve the resource utilization, which in turn improve the overall throughput and the performance of the system. So, with that I am concluding this multithreading concept, and in the next module we are going to look at multi-core architectures which exploit a thread level parallelization at a bigger scale. Thank you.